Welcome. Today we're going to talk about the properties of real numbers and closures of sets. So first let's talk about the property of numbers, of real numbers. So we all understand what real numbers are, right? They're the set of rational and irrational numbers. We've been over that before. There's the associative properties, there's the commutative properties, and the distributive property. So let's go over the associative property for addition. Says that, so this is for all real numbers A, B, and we may need C in just a minute. So the associative property says that if you are adding two things together like this, and a third thing together after that, okay, so this is saying adding two addends together, A, B first, and then adding C, is the same thing as adding A to the sum of B plus C. So in other words, this is saying that the order in which you add things doesn't matter. Okay, likewise, if we have A times B with a C outside, you can switch around the parentheses to have the A outside. Okay, I always remember associative because the word parentheses has an A in it, and the word associative starts with an A. Okay, so again, this means that order does not matter. Okay, the commutative property, I remember this as like commuting. I commute to work, so I move around where I am during the day. Okay, so this is what the commutative property says. It says A plus B is the same as B plus A. That with the addends, you can switch them around. The commutative property of multiplication says that A times B is equal to B times A. Now, both of these properties can be extended if you have any number of addends. So we could go A plus B plus C is equal to, we could do B plus C plus A, we could do A plus C plus B, okay? I can switch them around any way that I like. Likewise, this could also be used for two or more factors. So A times B times C, I could rearrange it in any way that I wanted to, okay? I could do B first, then C, then A. So it's just saying the order doesn't matter in which or the order in which I represent the factors or the addends doesn't matter here. Okay, distribution is the link between addition and multiplication, or you could think of addition, it's also subtraction. So multiplication distributes, so if you have a C on the outside and then a sum, that's the same thing as taking the C and multiplying it by both terms. So C times A plus C times B. Okay, and you can always rearrange that AC plus BC. Okay, so this also extends to subtraction. So if you had that, that would be AC minus BC. Okay, the next set of properties we're going to go over are the identity and the inverse properties. The identity properties is the thing that you add. So in addition, it's the thing that you add that you can add to any number in order to get to zero. So we say, the thing that you add to any number in order to get the number back itself. So our identity in addition is zero because so in addition our identity is zero because A plus zero always gets you back A. In multiplication, our identity is 1 because A times 1 gets you A back. So an identity is anything that you can operate on a number and get the number back. Okay. The inverse property is the number that you add to another number in order to get to the identity, which is either 0 or 1. So here, our inverse in addition is always going to be the number's opposite, because A plus negative A is equal to 0. And see, this gets back to the identity. 0 is the identity in addition. Now, the multiplication, the inverse of multiplication is it's reciprocal, because A times 1 over A is equal to 1. And remember, 1 is the identity, so 1 here is the identity for multiplication. So it's any number that you can operate, use either addition or multiplication on the other number in order to get back to the identity. That's the definition of the inverse. Okay, so another concept here is the closure. Okay, a set of numbers is closed under an operation if the result of the operation on any two numbers in the set is also a number in the set. So a set is just a collection. So for us, the set that we're going to go through an example here, and the set that we're going to use is the integers. So what this means is that I'm looking at the integers and I'm wondering, are they closed under addition? Okay, so this is sort of a question. Are they closed under addition? Well, let's think about what this means. The result of the operations, so the result of addition on any two numbers in the set of integers is also an integer. Okay, so the integers are closed under addition if I can take any two integers and add them together and get another integer. Okay, so let's think about this. So if I take an integer, -2, and I add it to another integer, 3, I get back 1. Okay, 1's an integer. Okay, let's take a 0 plus 0 gets you 0. 0 is also an integer. I can add two negative numbers together and get back a negative number, but that's also an integer. I can add two positive numbers together and get back a positive number, but that's also an integer. So any integer I add to another integer, whether it's a different integer or it's the same integer, okay, I always get an integer back. So a set of numbers is closed under an operation. So for us, integers are closed under addition. We no longer have to use this question mark. They're closed under addition because the result of addition on any two integers is the number in the set is also an integer. So I've taken the definition and I've made it a little bit more specific to our case here. So let's go over another example. Okay, so we're looking at a set of numbers. It's not like a giant set. It's just a set of -1, 0, and 1. Okay, and this is stating that this set is not closed under addition. So there's a lot of different things we got to try. We have to try adding every number in the set to another number in the set. We got to add 0 plus 1, and then we got to add the numbers to themselves. 0 plus 0 and -1 plus 1. Okay, let's think about the results here. So if this is all the combination of one number with another number and one number with itself, right? -1 plus 0, -1 plus 1, 1 plus 0, and then the number with itself. Okay, this would be -1, 0, 1. This right here would be -2, 0, and 0. So it's closed if upon operating, so when I say operating, in this case, I mean addition, if I can add every number in the set and get another number in the set. Well, the problem is here, this -2. -2 is not a number in the set. So -1 plus -1 gets you a number that's not in the set. So this set is not closed under the operation of addition. Okay, if I looked at the set under multiplication, however, so if I say, okay, look at this set here, and I were multiplying everything together, so -1 times 0, let's try this. Let's see if it's closed under multiplication. So this would be 0 times 0 and 1 times 1. Okay, every combination of a number with another number or a number in itself under the operation. Okay, this would be 0, -1, 0, 1, 0, 1. Okay, so this number only 0 is in the set, -1 is in the set, 0 is in the set, 1 is in the set, 0 is in the set, and 1 is also in the set. Okay, so all the numbers, when I choose these numbers in the set and I use it multiplication, then they get another number back in the set. So this set is closed under multiplication. So this is the last example here. The set of irrational numbers is not closed under addition. Now this seems really strange because let's think about irrational numbers. We have like square root of 2 plus, let's say, the square root of 3. Well, the only way we could write that is just the square root of 2 plus the square root of 3. There's no way to simplify that because their radicands aren't alike. So really what this means is, okay, this is irrational. If you add it together to another irrational number, you actually just get an irrational number Because think about it, if this decimal didn't terminate or repeat, this decimal didn't terminate or repeat, when you add the decimals together, you're going to get another decimal that doesn't terminate and doesn't repeat, thus it is irrational. Okay, but the trick is, so negative 2 is an irrational number. What if you added to itself its opposite? Both of them are irrational, right? Negative 2 is irrational because a decimal doesn't terminate or repeat. Same with its opposite. If you add those two together, what do you get? 0. But 0 is a rational number. So this is the only situation. If you take an irrational number and you add it to itself, you get a rational number of 0. So just because there exists one situation in which you can add an irrational number together with another irrational number and get a rational number, there exists one case in which you can do that. You can say that it is not closed under addition. Okay, if there's at least one situation in which you can operate on two numbers in the set and get another number that's not in the set, then it's not closed. Closed means that it's like bound. It can't be, you can't jump out of the set, okay? Let's look at irrational numbers under multiplication. So if I took an irrational number and another irrational number, let's say the square root of 3, or let's say, what if we did the square root of 2 times the square root of 2? Okay, well, that's going to be the square root of 2 squared, but isn't that just 2? Right? So the irrational number times an irrational number gets you a number that's not irrational. So the irrational numbers are not closed under multiplication either, because I can think of a number, I can think of two numbers, they're not unique numbers, they're the same number, that when I multiply them together, I get another number that's not in the set. Okay? Now, the trick with closure is that you just have to prove it for one situation. I could take two other irrational numbers, like pi times pi. Well, that's pi squared, and this is an irrational number right here. Okay? So just because it doesn't work in every case doesn't mean that it's not closed. Closed means I take a number in the set, I operate on another number in the set, and there exists at least one situation in which it pops, the number that gets out is outside of the set that you were looking at. Okay? So I'm going to ask you a few questions about this, and we'll work on this tomorrow in class. All right? That's the end of the lesson.